This is going to be my last take at recording this lesson, so if it is a mess, I apologize, but I am not backing this video up to record it again. So welcome to Algebra 2. We are in our review day lessons, so we're starting to review for your EOC, but we do have some content left that we need to cover, and so the approach that I'm taking this year is we are going to roll some of that new material into our review days. So this lesson is going to cover an intro to asymptotes, which is one of my favorite math vocabulary words, and also hit on some of the mock EOC problems and how we can approach solving those problems or answering those questions using the resources that we have. So we're going to talk about asymptotes, one of my favorite math vocab words because it sounds like you're saying something naughty, but you're not really saying anything naughty. It is asymptotes. A singular would be asymptote without the S. I went to graduate school with a student who used to say this word asthmatope, which is wrong. It's asymptote is how we would say the word. So let's get into this. This is part of a unit on rational functions. So we want to start with that question. What is a rational function? This is that last unit that we need to cover before your EOC, and we're going to highlight some of the key things about rational functions. So what is one? A rational function is a function that can be written as a polynomial divided by another polynomial, which of course assumes that you know what a polynomial is. That is defined in a much earlier lesson, like December or something. We defined what a polynomial is. Now, the word rational contains the word ratio. You can actually see it in there. And so if you remember, a ratio is a comparison of numbers. And so we write those as, there's a bunch of different ways you can write a ratio, but the most common way that we see them written in math is as fractions. And so rational contains the word ratio. And so the function will be a fraction. So here are some examples. You could have a linear function or polynomial, because a line is a simple kind of polynomial, divided by, let's see, a quadratic. So negative 2x squared minus 2x plus 15. Okay, so that would be a linear divided by a quadratic. But it could be any kind of polynomial divided by any kind of polynomial. So we could have, say, a cubic 2x squared minus x plus 1 divided by a quadratic. We'll say x squared minus 4. Now, it's kind of interesting to play around with Desmos with these to look at the graphs. These graphs are going to have some attributes that are unique to them that we don't see in other kinds of functions that we graphed. And one of those is this concept of an asymptote. Okay, now we have seen asymptotes before. We actually see them in our like exponential functions, but I don't usually spend a lot of time talking about them in the exponentials. So for most of my students, this will be a new concept unique to this. So what we have here is we're going to start with something called a reciprocal function. So the examples that I gave you on the previous slide are good examples, but they're also kind of complex examples. So a simple rational function that's good to start with is something called a reciprocal function. So if you've got the copy of the notes for this, a reciprocal function is just f of x is equal to 1 over x. And so that's a really simple polynomial, like a constant 1 over a linear polynomial. So we have a constant over a linear, and it's a really boring linear polynomial. It's just x. Now, what we're interested in, though, is what does that look like? So what are some of the attributes of this graph? So I'm going to go put that in as y equals 1 over x. And I want you to notice some things about this graph. So let's see if I can find my pointer. Okay, I didn't mean to do that, but I did. So Yep. Okay. So, what did I say at the beginning? I said I am not redoing this. So, I'm going to put that up there so you guys can see what it looked like. Hopefully you got a good look. You guys are on a video though, so you can go rewind it if you want. It looked something like this. And of course, I click through it anyway. So the graph comes in two parts here, and I mentioned that. So you've got like this part hanging out down here, and then you have this part hanging out up here. And what you might notice is that there's like a trend to these. And so if you look at where the x-axis is right here, you've got this piece of the graph, and it looks like it's getting closer and closer and closer to the x-axis. And then over here on the left, you've got something similar going on where it looks like it's getting closer and closer and closer to the x-axis. And then we have the same thing going on with the y-axis, where it looks like the graph is kind of just getting steeper and steeper and steeper, but also getting closer and closer to the y-axis. And that is our first glimmer at, I gotta make sure I click on the right thing here, on what an asymptote is. So a key feature of rational functions is something called an asymptote. And that is a line that the graph approaches but never reaches. It never gets to the line. So it gets closer and closer and closer and closer. Now, when I teach this in class, I have an illustration. I call it Escape from Algebra 2. And so we're like all trapped in Algebra 2 together. We want to escape. And there's the door. So now, when I do this in class, we will actually have somebody do this. But my classroom, so like here's the front of my classroom. Here's my whiteboard. Here's my desk. And here's the door, okay? And here's all of you sitting in my classroom. And so we want to escape from Algebra 2. So here's how this works. Here's you, okay? And you're standing a certain distance away from the door. And I say, okay, to escape from Algebra 2, you are going to head towards the door. But before you can get all the way to the door, you have to reach the halfway point, which might be right about here. And so here's our halfway point. And then we basically are going to repeat this. So now you're standing a little bit closer to the door, and you still want to get out, but before you can get all the way there, you have to cover half the distance. Before you can cover the whole distance, you have to cover half the distance. So that's going to put you right about there. And so we're closer. And then we can do that again. We still want to get out the door, escape from Algebra 2. Okay, we want to get out of here. But before we can get all the way to the door, we have to be able to get halfway to the door. And what happens is that, and usually about this point in time, students can kind of see what's going on here, is that we're going to get closer and closer and closer to the door every time we carry this out, but we're never going to get to the door. Now, practically speaking, there is a limit to how small of a step we can take. We will get down to a distance that's so small that we actually can't move our feet to get to half of the distance. But mathematically, no matter how small the distance is, you can still divide it by 2 and go halfway. And then you get a smaller number, but that smaller number can still be divided by 2, and you can get an even smaller number. And that smaller number can be divided by 2. This gets into the idea of a limit, okay? And for those of you that go on to pre-calculus, that's kind of where pre-calculus like ends with limits and is where calculus starts. And this is really your first intro to this idea that there's a limit to where this can go. So if I look at this example, okay, from my kind of, I clicked through it too fast slide, hopefully I won't do that again, is that this graph keeps getting closer and closer and closer and closer to the x-axis, but it never actually gets there. okay, because it's doing something like our escape from algebra 2, which the point of the exercise, by the way, is that you can't escape from algebra 2. You are stuck. None of us will ever get out. But that's the idea, okay? And we have what's here called a vertical asymptote, meaning the graph is getting closer and closer to the y-axis, but it never actually reaches the y-axis. So the point of today's lesson is to introduce what an asymptote is, what it looks like, and then how it relates to this very simple function called a reciprocal function. And then what we'll do in some of our future lessons heading up to your EOC is we'll look at how can you tell from looking at a graph or looking at the equation where the asymptotes are going to be. All right, so okay, so let's take a look at these with a reciprocal function. So I want to approach this first by looking at the transformations. And again, we're gearing up for your review for your EOC. And so reviewing those transformations is important. So remember with our functions and our transformations, we have things that are always consistent, like a negative flips the function over, okay? We have an inside number that controls the left and the right. We have an outside number that controls the up and the down. So when you're looking at a new family of functions, mostly you need to know where is my inside and where is my outside. With a reciprocal function, the inside would be the inside of the fraction and the outside would be the outside of the fraction. So subtracting a 5 on the inside means we would move this right 5 units. Adding a 4 on the outside means it would go up 4 from the position of the parent graph. So let's go check that out and then we'll see. So I'm going to put the parent function up there again. Try not to like go, click through it. And there's that graph again. Okay, and you can see the asymptotes, I think, are the idea that it's approaching these lines better. Now let's look at this one. Now this one, remember, we're going to compare it to the parent, and it should go to the right 5 and up 4. So I equals 1 over x minus 5. There's that to the right 5, and then up 4. And you can kind of see why we don't start teaching transformations with graphs that look like this, because it is harder to see. It is legitimately harder for us to see what that transformation is. You're kind of looking, let me see if I can turn my pointer on. You're kind of looking at this like central part, here, but there's no dot there. It's not like the vertex of the absolute value function where you can like really see where the point goes. But it does go to the right 5 and up 4. So it would be right where my laser pointer is sitting. And so we can see that transformation is what we think it is. Now, what are the asymptotes here? So the asymptotes are, in this case, vertical and horizontal lines. Now, there are things called oblique asymptotes, and those are asymptotes that are at an angle, and you can find those by doing some polynomial division. But if I look at the blue function, so I'm going to go ahead and hide the red one there. I have what's called a horizontal asymptote at y is equal to 4. And now that I graph that in there, you can see it like, oh, it is getting closer and closer and closer to that green line, but not ever touching it. And then I have a vertical asymptote at x equals 5, and that is showing on that purple. And so if you were asked what are the asymptotes of this function, you would say there's a horizontal asymptote at y equals 4. It is called a horizontal asymptote because the line is horizontal. And we have a vertical asymptote at x is equal to 5, called vertical because the line goes up and down. Now, like I said, in a future lesson, we'll get into, at the very least, how to find the vertical ones. Vertical ones, I actually think they're more work than the horizontal ones, but the horizontal ones take a lot more explaining. Once you know how the horizontal ones work, they're actually easier to find most of the time, as long as your polynomials are in standard form, than the vertical ones. But it, like, actually explaining it in a way that will work is kind of involved. But for now, we just want to focus on this idea of the reciprocal function, what that graph looks like, and then what the asymptotes are and how you would see the asymptotes on the graph. And that's our goal for today. I do want to point out that the green and the purple are not a part of the graph, okay? They are the asymptotes, but they're not a part of the graph itself. So if I go to hide them, that is the graph. The others were so you could see the lines of the asymptotes. So asymptotes are not a part of the graph, but they are a feature that's used to describe what the graph does. Kind of like the axis of symmetry for a parabola. The axis of symmetry is not a part of the parabola, but it is a useful feature. It's useful for us to look at, especially if we're trying to graph something. Okay, so that was it for the new material. I lost my little timer, so I have no idea how long that took, but that was it. You know, we're going to take that key Unit 7 information in some bite-sized chunks there. And now we're going to take time to start the mock EOC, review the questions, and review questions as we go. Now, this is more of an in-class note, like pay attention. Oh, sorry. Pay attention to when we go over how to do the problems and make notes. At the time I'm recording this, I'm not sure if I'm going to give you guys like a big chunk, like do 6 problems and then we'll review all 6 problems, or if I want to give you like 1 or 2 problems and then go over the 1 or 2 problems. Like, I'm not totally sure how we're going to break that up. So if you are going to be in class, just pay attention to how that's going to work. Now, if you're doing this at home, I do want you to try, like, pause the video, actually pause the video and take a look at this, like pretend this is a question on your EOC, and you'll notice I have Desmos up there, and yeah, the Desmos is up there, but I want you to kind of work this out and decide on which one of those answer choices you would select. So pause the video and go ahead and do that. Okay, hopefully you did that. Now, I actually worked this one out earlier because I like quadratics. I'm cool with quadratics and I don't mind solving them. You can solve this using substitution. You can use it probably using different kinds of strategies, but this is one where graphing is going to come in handy. And we did cover systems this year. It was an assignment that I think back in November when I had to take a trip somewhere, and I put together these like big lessons for you to cover on your own, and most of you did them just fine. But probably the best way to solve this system is to use Desmos. So we would graph both of them and we'd look to see where they intersect. So I'm going to open up my graphing calculator. One of the things that's great about Desmos is you don't have to solve equations for y in order to be able to graph them. Your graphing calculators, you do need to solve them for y before you can put them in, but Desmos, you don't. So you can just type that in as is. And then we'll do the next one, minus 2x minus 11. And then we're looking for where the graphs intersect. We're looking for the values of x and y. Just to kind of go back over the content, remember that the graph of an equation is the set of points, or is the values of the variables that make the equation true. So the graph for this are the values of x and y that when you put them into that equation are going to give you 5 = 5. And if you look at the graph for it, there's an infinite number of red points. They're all over the place in that equation or in that graph. Then the blue would be the same for the second equation. It's all of the x and y's that make the second equation true. Okay, so you would end up with something equals itself. The solution to the system would be the set of points that work for both. And so you would be looking for where the blue graph and the red graph intersect. So I see an intersection point at 3, 1, and then one down here at -1, -7, which means that we are picking answer choice C for this one. Now, notice some of those distractor choices. Notice the kinds of things that, yeah, so we've got 2 in there. I'm not sure what's at the 2. I've got the little, my face is kind of covering it up there. But we have like the point 1, 3 and 7, -1. 1, 3 might be like not knowing which of those coordinates comes first. The 2 probably comes from a mistake from if you were to do this algebraically, you could get a 2 dumped out. If you're wondering about this first one though, that first answer choice is what's called the empty set, and that would mean there are no solutions. So you would pick that if you graphed like the parabola was up here and the line was going below it, and there was obviously no way that the parabola and the line were ever going to intersect, you would pick this. It's called the empty set. It means that there's nothing in there. Okay, now there are other ways to do this, but Desmos is about as good of a method as you're going to get with this. So I would highly recommend for a system that you would use Desmos. Now this one, we have the product, and you could conceivably use Desmos to do this problem, but my personal take on that is that it's not the best way to do it. So what you could do is you could put the product in like y equals, and then it's kind of highlighted gray. I'm not sure why it's highlighted gray. That has something to do with how I clicked on the document when I put it into the PowerPoint. But and then you could graph each of the answer choices to see which one of the answer choices match the graph. So you do like y equals, and then the first line, and then y equals answer choice A, y equals answer choice B. Now that'll work, but it's going to take you a long time. So even though you have access to Desmos, and Desmos is a valid strategy for a lot of these, it's not always the best strategy. So this one is probably quicker if you just multiply it out. So we have 4x plus 1, -x², 3x minus 19. And I'm going to just show you something that I would do. In fact, when I was looking at this problem earlier, I multiplied the corners. So I said, okay, 4x times -x² is -4x to the third. And then 1 times -19 is -19. Based off of that, I am not picking B and I'm not picking A, because A does not have the correct leading term or units term either, and B does not have the correct constant term at the end. So I know, because I know how the area model works, that those two have to be the same. So if I'm running out of time, okay, like I'm really running out of time, I'm not going to pick those two. Those two I can do pretty quickly. You could even do them just trying to distribute a little bit. Now let's take a look at the rest of them. So this would be -x², 1 times -x². This is 12x², and we can probably answer the question right there. We don't even have to finish the problem. 12x² minus x² would give me 11x², which means that, I should probably change my color back, that that doesn't work. It's got to be answer choice C again. And that's the beauty of the multiple choice. It's not so much that you're going to use decimals for everything or that you can just randomly guess, but you can actually do a lot of problems and only do them part way through. You don't have to finish it, because look at this last term here, like the one that we don't have. It's big. Okay. Whatever that is, that's like your 19 times the 4 there. That's going to be big. If I can avoid doing that, if I can save myself the time and the trouble of doing 4 times 19, I will. And I can, because I can do the quadratic term. No. Just sit over. No, you know, you're a good cat, but you're gonna be in the way. He's not listening. Say hello to everybody. Look at the camera. Look at the camera. Say hello. I don't want to say hello. Okay. Why don't you go? Like, just go. Okay. He's not following directions. Yeah. All right. But just to see the rest of it, we would have positive 3x here. And this is, what is this? 19 times 4. This is 36. Like negative 76x. And then those would combine to give me the negative 73. But again, notice on that how you don't have to do the whole problem, and how Desmos, if you had to type all of these into Desmos, it would very likely take you longer. Okay, so note that one. I think on the last one, I forgot to tell you to pause the video to work it out on your own. Now you'll notice I don't have Desmos on the screen, which means that I think this problem can be done best without Desmos. Now you certainly could use it. So, but pause the video, do what you need to do, select your answer, and then unpause it when you're ready to talk about it. No, but okay. All right. Sorry, there's like a cat. He's like laying right across my lap, not on the keyboard, but he's perilously close to the touchpad. So. Okay, moving on. So now, things to notice as we look at this. I'm going to point out some stuff that I note. Notice that the -1, x -1, x -1, x -1, and then the -3, -3, -3, -3 is the same for all of them. Something that I would look for is I would look for the position of the parabola. So we know that that means the parabola is going to go right 1 and down 3. And so I would check that and look at where the parabola is. Like, and indeed, if you look at the coordinates of the vertex there, it is right 1 down 3. So in this case, that does not eliminate an answer choice, but it could in another problem. It just, in this one, it doesn't. So we need to look elsewhere for what we can eliminate. So here's some things to remember. A dashed line means that you have the greater than or equal to, but or greater than or less than without the equal to. A solid line means that you'll have the equal to. So because this is a dashed curve, I know that it's not going to be either of those, because that symbol there would give me the solid one. Now that should not be a random fact that you're just trying to memorize, okay? If you had an equal sign, you would have a solid line, or in this case, a parabola. Okay, if any of you, like, you put it into Desmos or something, if it was equal, it would be solid. We've never had an equal sign, and we just decided to do it dashed. So anytime you're seeing the equal, means it's going to be solid. Okay, so again, if you're just trying to memorize some random, like, I can't remember when it's dashed and when it's not, think about what you do know. Like, we've never had something with an equal sign that has come up as a dash line, like, ever. So that's it. It's when the equal part is missing. That's when you have it dashed. So now if you had to guess, all right, you could better your chances by a lot by eliminating 2. So now when we look at what makes them different, one of them is less than and one of them is greater than. And notice what's less than. Y is less than or Y is greater than. Well, there's my Y axis. If Y is less than is going to be towards the bottom. If Y is greater than, it's going to be going towards the top. So look at where this is shaded. It is shaded above the parabola. Below the parabola is not shaded. So it is the greater than that is shaded, which means we're going to be picking answer choice D. Now, you can do this. I obviously I didn't put Desmos up here. I thought we can do this faster without checking out Desmos. But you could put in all of those inequalities to find the one that matched the graph. The problem with falling back on that too quickly is that you're going to run out of time. You still have a time limit for answering these questions. So it is critical that you're using Desmos when Desmos is the best option, or when you know you have enough time to use it, but that you're not falling back on Desmos for problems where there's a better way. You know, a compromise might be if you can eliminate A and C because of the wrong symbol and then kick over to Desmos because you can't remember which way you're supposed to shade it, that would still save you time. And that's kind of hybriding the two strategies together to leverage like the piece of information you know or the piece that you don't. But you do need to look at each question and determine whether or not Desmos is the best option for you to use. So this one, I actually would do something separate here. I think where because I something jumps out at me. Now for most of you though, I think this is gonna need to be just like straight on Desmos. I think we're just gonna put it in and see what we see. But something I notice is if I look at these two right here, okay, see how these two are right here? And you've got a negative and a positive. Now I know those are yucky numbers, but negative and a positive. I know without any doubt that 0 is between these numbers. So if I go and plug in a 0, I have 6 times 0 is 0 minus 0. So I have 0 is less than 12, which is true. I know that one of these has to be the correct answer. It's not these two because they're because of the way they're doing it, they're doing everything to the left and they're stopping at the negative number and then they're jumping over to a positive number and then going everything to the right, and they're doing the same thing over here. So they're jumping over to the 0, and I know 0 works. So if I had to guess really quickly, I would pick either B or C. And that is something that I notice to do. Those are the kinds of things that make the difference between like a great test and like an okay test. But let's go ahead and put that in. So minus x is less than 12. Okay, and notice how it is shaded in the middle. Okay, which means that it's not shaded out here towards negative infinity. Negative infinity would be out there by the 10, and it's not, and it's not stopping here. It's one of the middle ones. That's kind of what I was just alluding to. I know that 0 worked. Therefore, it has to be one of the other two. And let's go see if we can find that. That is negative 1.33333 and 1.5. Now, yeah, if you don't know what those are, Okay, Desmos can help you out a little bit. So you can put 1.5 in and it'll give you that little fraction, okay, and tell you the 3/2. So this number over here was the 3/2, which means that it has to be answer choice B. I'm not totally sure what Desmos will do with the negative 1.333. It's going to offer it, but I think it's going to give me something messy. Yeah, it's not registering that it's like repeating forever. So, but the 1.5 is okay. So the 1.5 was, oh, wait a minute, was this one. It was over here at the 1.5, which we now know is 3/2. So it stops at the 3/2, which means B needs to be our answer choice. And I am not being very consistent with when I'm telling you guys to pause the video to work them out. So I hope you know you should pause all of these and work them out and just see what you can do on your own. All right, another one with Desmos. So this time I'll remember to say it. Pause the video and check out, like, how would you answer this, which is not a solution to the equation below. And then unpause the video and let's check out what we would do. All right. Now, there's two ways you can do this. For a lot of you, you can put the equation in there. So you can actually dump it in and, okay, oh, wait a minute. Oh, 63 equals 0. And it gives you these vertical lines that you can then go, actually, I think that's the drawback. So you can click them, but yeah, you can't actually click on what those points are. So in this case, that's probably fine. You've got like the 3, so the 3 works, and then you have the -3 and the -7. So +9, which would be over here right above my head, does not work. But if this were something that had some fractions, if the numbers were yucky decimals or fractions or something, and it wasn't something you can count, here's what you can do. Instead of making it equal to 0, make it equal to y, which turns it into a polynomial, and then you're able to actually click on those points, which again, for something like this that are these nice integers, it's not a big deal. But if it were messy numbers, that would be your workaround, is just graph it as y equals, and then you're looking for where like the y would be equal to 0, which of course is the x-intercepts. So which one is not represented? That would be the 9. So we are choosing answer choice A on that problem. Oh, my cat got tired of sitting on my lap. He's going to go sit on a stack of homework I need to grade, so he's helpful. I had to come home early today, so normally I would try to do this at work. It's like a little less distracting. All right, we're almost done. Now this one, this is an absolute value inequality. We did do this in class, but it is one of the more challenging skills, not just to execute, but also to get your head around. So you notice I have Desmos up. I recommend Desmos is probably the way we want to go. So pause the video and see what you can see. All right. So let's go explore this, and maybe if I can see, oh, I gotta turn my pen off. Okay, so let's open this up. All right, so you can do, the absolute value symbols are in our toolkit right here. So you can do that. You can also type ABS. I'll do a couple of them just so you can see. So if we have 4x minus 13, and then now I got impatient with this when I did it the other day. because I don't like to continue opening this up just to get a symbol. Like, I just don't want to keep doing it. So I was doing it with just the less than and greater than because I can get it on the keyboard, and it doesn't really affect my answer. Now, take a look at where we are. So here's the 0, and then the break in the graph is over to the right of the 0, which if I look here, the break in the graph is to the left of the 0. So it's not that. Now, what I would recommend doing is leaving this there. So you cross off A, you're like, okay, I'm not picking A. And then instead of trying to retype everything, but I did want to show you this. If you like the keyboard better, you can type ABS and then put it in like so. And then we would need less than or equal to 7. Oh, and let's make that. Yeah, like make that. Okay, now this one is over on the right, and instead of, it's like inverted. It's completely inverted from what we want. So we've got it like the graph is in between, but it's still happening over to the right of the 0. And what we want is like everything to the left and everything to the right, and we want the break in the middle. Now, again, this is what I was saying about saving yourself some time. Instead of retyping it every time, once you've eliminated answer choice, just go back and edit it. So I'm going to go ahead and edit this one down here. Well, I'm going to get rid of that one. So we're going to edit this and change the minus sign to a plus sign. Oh, I have it invisible. There we go. And this I like. Okay, I like where this is. It's at the -5. It matches up what I have out there, and it's got the break in the graph in the right spot. And so I'm liking answer choice C for this. Answer choice D would just flip the inequality around. And yeah, that's not what we wanted. We wanted the break in the graph to be there, not the graph itself, with the breaks on either side, I guess, so to speak. So let's go ahead and there we go. So I just kind of want to end the screen with it like that. And so C is the one that matches. Again, this one, we have covered it, but it's challenging. It is challenging. The mechanics of the algebra is challenging. I think this one is definitely one that you can answer more quickly and with more confidence using Desmos. And that's really the game here, is we want to be able to use Desmos, but we also want to make sure that we're using Desmos in the best possible way. And we're not using it for like the multiplication problem that's actually easier to solve without it. And I think this is my last one for this lesson. So a certain quadratic function has a vertex at 2, -3 and passes through the point 0, -5. Which of the following equations could be used to model the function? There are 2 ways to do this. I'm going to go over both ways, but I do want you to take a moment and see if you can figure it out on your own first. So pause the video, settle on your answer choice, and then unpause the video, and we'll look at some different ways to do it. All right, so let's take a look. Now to do this, either way, we need to get both of those points onto our graph. So I'm going to click my add item, and I'm going to click table, and I'm going to go ahead and put in 2, -3 and 0, -5. Now, the first way that we can do this is we can do this by using a regression. Now, before we use the regression, I need to get my laser pointer back here. We need to make sure we're paying attention to which point is the vertex. The vertex is 2, -3. So follow my pointer. That's the vertex, which means the parabola does this. That's got to be the turning point. If you pick the wrong point, you'll have a parabola doing this, which is not the right parabola. So we want to do this. To do a regression, we really need to have another point. And so if we remember that parabolas are symmetrical, I know that if 0, -5 is on the parabola, this point right here, right at the edge of where my video is, that also needs to be on this parabola. And so that would be the point for -5. So I'm going to come over here and put in the point for -5. And you can like check and make sure like, yes, that point is where I wanted, but you have to pay attention to which point is the vertex. Now to do a regression, we need to use x1 and y1, okay? And we need to use that little tilde instead of an equal sign. Now, notice my answer choices. Some of my answer choices are in standard form and some of them are in vertex form. And when I did this problem earlier, I totally wasn't paying attention. And so I did the regression in vertex form, which would look like this. Y1 tilde, and then we have A, x1 minus h all squared plus k. And if you want to write that down as part of the review, that's your vertex form. And what I notice is that the A value has to be -1/2. So C and D are the ones that are in vertex form. So if you're like, I don't remember what vertex form is, how am I supposed to remember that? Look at C and D. C and D are in vertex form. So I can eliminate answer choice C because this number, the A value, is not the right number. And then it says my H value is 2, which means that I should have x minus 2 because it's x minus h. So that's going to eliminate that. You could also do this with your transformations. A +2 inside the parentheses there means it should go left 2 and like down 3. And it's not going left 2, down 3. It's going right 2 and down 3. So you could eliminate it that way. And that's when earlier when I was doing this, I was like, oh, wait a minute. 2 of them are in standard form. So we can also do a quadratic regression in, I just don't want to click the wrong thing. It is not